all-in selection, and then generate a solid core based on that selection. So I can open the solid core dialog and change the shape and drag the height and values of this solid core. When I'm happy with that, I can OK it. And then, if I blank the model from view, we can see the solid core that we've extracted from our model. I'm going to make sure this solid is active, and then I'm going to use some of our solid editing tools to start to fix this model. So I can delete the top portion, as I don't want it. And if we look, we have some filleting surfaces that we also don't need. I'm just going to select those surfaces and then use the solid healing function to remove those surfaces. I can tangentially extend all of the burn regions. And then, when I've finished extending the burn regions, we can start to look at passing this into the electrode wizard. So we'll make sure the main model is active, select the electrode, and then start the electrode wizard. The first thing it's going to ask is if we want to add a base to the electrode. So it could be that the user has designed a base. I haven't in this case, so I'm going to let the electrode look into the library and pick the most suitable size base dependent on the size of the electrode I've designed. So we have a range of bases in our library. Alternatively, the user could specify their own dimensions. Next, we're going to specify the holder that we'll be using. Again, this will look into the customer's library and offer holders that are suitable for this electrode. So I'm going to pick the holder. If we zoom out, we can see the electrode and the holder being assembled on the model. Click Next, we're specifying the name and the counter and whether we want to generate a setup sheet. And on this page, we have a series of standard catalogues to specify our spark gap sizes. So in this case, I'm going to use the OPS Ingersoll catalogue, but I'm going to give it user-defined values. So I'm going to create 2 electrodes, one for roughing, one for finishing, and these are the spark gaps that I'm going to give it. We can click Next. I'm going to export all of the data that I need for PowerMill. Here's my export location. I'm going to generate the script file for the EDM machine, and I also want to add some points that I can use for inspection in Power Inspect. So I'm going to click on this icon, and I can define the probe radius I'll be using in Power Inspect. I can pick points around the electrode that I wish to inspect. So I can pick some also on the main form of the electrode. So I'll place one there, and we'll place one on the other side. And also one more on the top. When I'm happy with the points, I can accept them, and all of those will be stored into the trode file, which we'll see used in a moment. I'm then going to finish this, and this will save all of the data, export the trode file, and also we'll see a series of setup sheets generated. PowerShape asks if I want to create another electrode, which I don't. I can see the setup sheet, and this can all be customized to the user. So it's showing me the electrode. We have a detailed setup sheet where I can see the electrode and its position. And we can return to the main window, see the electrode, shade it to identify the burn regions, and we can also simulate the burning of this electrode. We simulate burning this electrode into the model on the EDM machine. Once we've designed the electrode, the next stage would be to machine the electrode. So we can come into PowerMill and use PowerMill's electrode wizard to help us automate the generation of the toolpaths. So I'm going to say extract an electrode. I need to navigate to the file that we just created. So I'm going to find it in the trode data. We can see the electrode, and I need to specify an output folder. I can accept that, and that will automatically start the wizard. So the wizard has been started and generated some stock, but we also see the Explorer window has loaded a HTML file that gives us all of the detail about the electrode. So we'll zoom in to the electrode wizard and click Next. We can use the analysis tools to identify small radii that may be difficult to machine, or identify any undercut regions, i.e. regions with a negative draft angle. And on the next stage, we can see that PowerMill has automatically picked up the spark gap sizes that we specified in PowerShape. We also have a range of machining strategies. So if the user machines a type of an electrode on a regular basis, they save those toolpaths as a template file. When they bring in a similar electrode, they can load those templates and automate the machining of further or future electrodes. So I'll pick on any one of these strategies and it will automatically load all of those toolpaths and tools into PowerMill ready for calculation. So you can see it's loading in the tools, and if I look at any of these toolpaths, go into the settings and zoom in, we can see the thickness has automatically been applied based on the trode file. So we asked for a spark gap on this electrode of 0.2 millimeters. When we're happy with that, we can click Next, and when I click Finish, PowerMill will start to calculate all of those toolpaths and go through and build us an electrode project. Now whilst we wait for PowerMill to calculate the toolpaths, we'll have a look at the inspection wizard. So in Power Inspect, I can start the electrode inspection wizard and again browse to the relevant electrode file that we want to use. You'll see the electrode appears and I can select it. We'll click Next, and then we need to tell Power Inspect which electrode we're inspecting, because we have two, one for roughing and one for finishing. So once it's loaded, we can select Finisher, and that will automatically load the probe paths that you saw us generate inside PowerShape. So the probe paths are automatically being loaded and created. Once we have those, it's warning us to make sure that we've got the alignment correct. So I'm just going to lift that probe out of the way and zoom in. Now we don't have a CMM machine here with us for this demonstration, nor do we have the electrode, so we're going to simulate the measurement of this electrode, and I just need to check the alignment to do that simulation. I can then go to Run and run all of the probe paths. So you'll see it's simulating the inspection of this electrode on a CMM or using on-machine verification. You see the confetti getting generated as it's probing each point. Once we've finished running the probe paths, we can click Next. It asks whether we have run them. We get the green tick indicating that it's happy with the results. We don't want to do further inspection, so we can click Next to automatically generate an inspection report. So again, this report is fully customizable to each customer. They can have names, logos, etc. And we can see details about the results of the inspection and images of the inspection itself. So if I finish that, it will load all of that data into the trode file. If we come back into PowerMill, we'll see that we have a series of calculated toolpaths. So I've got a series of toolpaths calculated, and we've also automatically generated the NC programs. So if I specify a machine option file, so tell it what machine we're going to run on, I could then write that NC file. We could go in and have a look at that and see the G-code that we would then pass on to the machine tool to machine the electrode. The other file we have is a script file. So this is similar to G-code, but it is for EDM machines. So as well as machining and inspecting the electrode, we could pass this file to the EDM machine that would then go on to spark the relevant area of the model. So we've seen how by using the wizards in PowerShape, PowerMill and PowerInspect, we can take an electrode from design through machining into inspection and also control the EDM machine.